So continuing to talk about volumes of revolution, if the axis of rotation is not flush against the region, then what we're going to see is that we don't end up getting what we refer to as disks. There's going to be a kind of space in between. So what I want to focus on today is what to do about that. What's the resulting shape, and how can we construct a nice formula to deal with those situations. So what I'll look at here is this region that's highlighted in green. So it's bounded by two curves, f of x and g of x. So to consider, first of all, rotating it around a horizontal axis, what I want to look at is a slice. Then we're going to continue what we saw before. If I have a horizontal axis of rotation, I'm going to slice perpendicular to that axis, which means I'm going to slice vertically. So let's envision that here. So this could be xk minus 1, this could be xk, and we could think of here what would happen. We can again define delta x to be the length of our interval divided by n, and xk to be a plus k delta x. Same kind of setup we've had before. Now, what I want to think of is what would happen to this slice. So let's assume that I fit a right-hand scheme here on this, and we can make it almost a rectangle. So if I were to rotate this around the x-axis, then what's going to happen is you're going to get a cylinder with a kind of an empty cylinder in the middle in some sense. So this is going to be on its side. Maybe I'll put this here, and you're going to have this kind of outer edge and this kind of empty part here. Like this. So this is what we're terming here this washer. You're going to have this kind of thickness here that's from delta x. And to be clear, maybe to match this up, this has this kind of hollow center. So this center circle here is kind of empty. So one thing I want to address that will apply to both the horizontal and the vertical case is how do we find a formula for something like that shape? So let's, for the purposes here, let's consider two different radius values. So I'm going to use R1 to represent the smaller radius and R2 to represent the bigger radius. Then the way that you can find the volume of something like this is you can take pi times, whoops, went too far, pi times the bigger radius squared delta x. That would be if there was no hole in the middle, minus pi times the smaller radius squared delta x. So you take the volume of the big cylinder and then just cut out the cylinder in the middle. And then we can write that a little bit more concisely by recognizing that I can write this as the big radius squared minus the small radius squared. And that is multiplied by pi and delta x. So this is our general volume formula for what we're now calling a washer. So in this context here, the only thing that I'm going to add is that the radius values depend on the functions involved. So when you rotate this rectangle around the x-axis, notice that the big radius, in this case, is coming from f of xk. F of xk, that's the distance from this axis of rotation to this outer edge here that's the height. The small radius that represents the gap is the distance from this axis of rotation to this edge here, which is g of xk. So when we're thinking here of v sub k, that's approximately the washer. And again, it's approximate because I've chosen a particular x to represent the whole interval. So from my washer formula, I get pi times the outer radius, which is f of xk. We want to square that, minus the inner radius, g of xk squared, all times delta x. And again, we could sum all of those together to get an approximate volume. So sum all n washer volumes. And then let n go to infinity. And we're going to get a definite integral. So if I want to find a formula for the volume exactly, I'm taking, maybe I'll put this out, pi, again, just like the disk method, but I have a difference of square functions. And I'm going to use the bounds on x, a to b here. So this is going to be our formula for a washer method rotating around a horizontal axis. Now, it's important here that when we're thinking about which function is being subtracted from which, we have to really know where these lie in relation to the axis of rotation. So in this picture, the f of x function is further away from the x-axis than g of x. And so that's why they're oriented in the way they have here. Now, if I do the same thing and think about rotating around a vertical axis, just like we saw before, vertical axis of rotation tells me that I'm going to slice now horizontally. Think about this as yk and yk minus 1. And right away then I can think of delta y is the length of the y interval divided by n. Y sub k is c plus k delta y. And what we want to think of is a formula for v sub k. And importantly, same thing, I can fit a rectangle. So let me choose a right hand scheme again. And imagine that we're going to rotate that around now the y-axis. And I'm going to get a washer again. The only difference is it's going to be kind of what we have here laid on its side. And it's still going to have that same kind of formula. So we're going to get that the volume of that slice is roughly pi. And then we're going to take the outer radius squared minus the inner radius squared, all times delta y. Now, because we're going to integrate with respect to y, we need to reinterpret these functions as functions of y. And then also focus on which one's further away from the axis of rotation. In this picture, the f function is again also further away from the y-axis. So I'm going to write this then here as f inverse of yk. And the inner radius then is g inverse of yk. The approximation of the entire volume then would take the sum of these. Let's see if I can fit this. And then this is delta y. And sending n to infinity, we now get our volume as a definite integral. We integrate from c to d. Those are the y values. We take the square of the outer radius minus the square of the inner radius dy. So just like the disk method, we have to pay careful attention to whether or not we integrate with respect to x or y. But also, each time we have to make sure it's very clear what the outer radius is versus the inner radius. And I'll again suggest that I find it very, very helpful to graph the region once it's described before I start to construct my integrals. So to get a little practice with this, here's a scenario where we're given a region R, and then we just need to set up the integrals. So we're not going to evaluate them. But in each case, we get a different axis of rotation. And you'll see there's 6 different scenarios here. So the first thing I want to do is sketch the region. So we're looking at the first quadrant, and it's looking at what's bounded between y equals x and y equals x squared. So these are going to intersect, and so we just want the region between. So this is x squared, this is y equals x. So I know throughout this problem, I'm going to look at this region. That's my R. So one thing I know is going to be helpful is to really know where these intersect. So I can see that this is the origin, 0, 0. But also, to find where they intersect up here, we're solving where is x equal to x squared. That's where 0 is equal to x squared minus x times x minus 1. Well, that's going to happen when x is 0 or when x is 1. And when x is 1, both of these functions evaluate to y being 1. So that's going to help when we set this up. So the thing I want to establish in each case is, what do I integrate with respect to? That's the first thing I'm going to think of. So when I have axis of rotation, the x-axis, it's a horizontal axis. I'm going to integrate with respect to x. So right away, I can put in the bounds on x and just kind of keep in mind that that's going to involve an integral with respect to x. Now, this is going to give me a washer, and we're going to think about the kind of construction here. So the distance to the outer edge, in this case, is going to be y equals x. So that's going to mean that my outer radius is x. The inner radius is just the length here from the x-axis to this bottom function, x squared. So x squared is the inner radius. Now, the next part here says, do the same thing, but let's look at rotating around the y-axis. So one big change is that's going to mean that we integrate with respect to y. Again, it just so happens that the numerical bounds on y are the same as x here. Not always the case. And in this instance, notice that the outer radius actually comes from the curve, right? If I'm looking at the y-axis, the further curve here is y equals x squared. So that's changing the orientation of kind of inner curve and outer curve. The other thing we have to do is we have to be careful that we need to write these as functions of x. So of course, if y equals x, we can write that as x equals y. But here we want to write x equals the square root of y. So the outer radius is square root of y. And the inner radius here is y. So that's going to be how we construct it this way. Now, I'm going to continue with this here to also consider, what if we have an axis of rotation that is horizontal or vertical, but it's not one of our named axes, the y-axis, the x-axis, etc. So the line y equals -1, first of all, notice that's horizontal. It's a horizontal axis of rotation. So like part 1, I'm going to integrate with respect to x. Now, what's harder about this is we have to be a little bit careful to think about what the radius is. We can kind of build off of what we did in number 1. So in number 1, we had a similar relationship. So it's still the case that the straight line is further away from my axis of rotation than the curve. But they're both further away from the line y equals -1 than they are from the line y equals 0. So the way we think about this is we need to find, for instance, this distance to get my outer radius. Think about splitting that up. We know that this distance is y equals x. And we know that this distance, I should have chosen a different color, is, let's maybe put dark blue. This distance is 1. So the outer radius in this case is 1 plus x. And likewise, the inner radius is 1 plus x squared. So a lot of times the picture can kind of help to see that, to split it up. By the same token, if I rotate around the line x equals minus 2, again, this isn't to scale, it would be further out here, but just for reference, I'm going to kind of sketch something like this. Importantly, again, I know it's a vertical axis of rotation. So in finding the volume, I'm going to integrate with respect to y. And just like we saw before, this is going to be similar to number 2. It's still the curve that is the outer radius, and the straight line is the inner radius. But now our axis of rotation has been shifted a little bit further away. So likewise, if I want to find this distance, I can do that by splitting it up. I know that this distance is x, y equals x, and I know that this distance is 2. So the outer radius here should be 2 plus, sorry, I said y equals x, but this light blue line is actually y equals x squared. So I should add the 2 plus the light blue of square root of y. That's going to be my outer radius. 2 plus square root of y. And the inner radius is the same thing. You still have the same dark blue too, but we're going to stop when we hit x equals y. So it's 2 plus y. So what I want to point out that's similar in 3 and 4 is if your axis of rotation is to the left of your region or to below your region, you end up adding to your radius. So we added something to the radius value to reflect that change. Now, the last part here that I want to look at, these last two, what we're going to consider instead is being to the right or above the region. And what I might do is actually sketch this again. So the line y equals 4, just for reference, I'm going to sketch my region. So we're looking at something like this. So the line y equals 4 is up here. It's quite a bit up there, but it's a horizontal axis of rotation. So I integrate with respect to x. And what we want to think about is, again, how we would find the radius value. So this is y equals x squared. This is y equals x. And I've condensed my view, but we're going to assume that's y equals 4. So if I have this particular value of x, again, let's think about how we would evaluate the outer radius. So the outer radius would be this red length. So to find that, what we want to do is be constructed a little bit differently from what we saw before. So what I do know here is I know this distance. Of course, that's not part of the red line. The blue distance is x squared, y equals x squared, the light blue. But I also know this distance is 4. So one way to interpret the red length is you can take the full length of 4 and subtract the light blue length of x squared. So my radius here is 4 minus x squared. And likewise, to find the inner radius, I take the full length of 4 and I subtract y equals x. And so again, with my picture, it's helpful for me to kind of visualize the length I'm trying to find and think about how I can either break that up or associate it to things that I do know related to the function value. By the same token, if we were to rotate about the line x equals 1, whoops. well, x equals 1 is here, to the right of my region. And I can now focus on trying to, this is going to be too messy, so let's put it here so I can focus on a new picture. Okay, so first of all, vertical axis of rotation, I'm going to integrate with respect to y. And that means that I care about writing these as functions of y. So x equals y and x equals square root of y. Okay, so in this instance, my outer radius is coming from the straight line. So let's use these same kind of colors again. Suppose that you're looking at this y value. The outer radius, whoops, I wanted to use a different color, would be this length. Just like we did in number 5, I'm going to break that up in 2 ways. I know, use a different color, use light blue. I know this length is just the distance y. And I know this dark blue is 1. So if I take the dark blue and subtract the light blue, I'm left with the red. So we can take 1 minus y, and that's my radius. Likewise, to get the inner radius here, I can take 1 minus square root of y, and that's going to leave me with this distance. So that's how we set that up. Again, I'll kind of group 5 and 6 together. What we've observed here is that if you're above the region or to the right of the region, to get the radius, you should typically have to subtract something to get to that full value. And it's not that you have to memorize this, because what I was saying before is that drawing the picture, you can always kind of sketch on it and think about what things do we know in terms of our function and what length am I trying to find to get my radius.